Welcome to Let's Code Club. So I'm here with the usual distinguished crew of gophers and cryptographers. Thiago is here, hello.
Hello, John.
And we're still thinking about the kind of cryptographic password related stuff that we've been thinking about for a couple of weeks. So as you'll no doubt remember, we looked at randomness and what that means and how to get it. We looked at passwords and how to generate them. And we did a bit of thinking about how many passwords there might be for certain kinds of passwords, or more generally, if we think about keys, we talked about the idea of a key space, which is the set of all possible passwords, if you like. So just to recap then, we said we worked on our key package a little bit, and we developed a few useful functions. So one thing we said was, for a given character set, let's say the typable characters, how many, for a given length of key then, chosen from those characters, how many could there be? So that was the space function. So for example, if we had a 2-character password where we have about 100 typable characters, that should give us a key space of 10,000 possibilities. And it does. And we also said, suppose, if clearly the time it's going to take you to guess that password, assuming you don't get lucky, is related to the size of the space. So assuming you can guess keys at a uniform rate, we can work out from the key space how long it should take, shouldn't we? And we say on average, you're probably going to get the right answer about halfway through your guesses. So a useful way to think about how crackable a key is, if you want to put it in those terms, is, what's the median crack time that you should expect? And we talked about what some values for that might be, right? Like if you had a certain password and you wanted to know how strong it is, you could say, well, what's the median crack time? 15 minutes on a typical laptop. That's probably not really that strong, is it? So, of course, it depends how much compute power you can throw at it. And we decided that, in fact, we can express that as being dependent on something called the try rate. So if you can try 1 million passwords a second, that's your try rate is 1 million. And so just for the test, we said, suppose you can only try 1 a second, you had a rather elderly computer. And we know the key space for this is 10,000. So it should take on average 5,000 tries, shouldn't it? And that 1 try a second, that should be 5,000 seconds. Pretty reasonable, isn't it? And we said, could we combine these things to ask if a given password is strong enough? So that would say, for a given try rate, we would say, let's say we want it to be safe for 100 years from a reasonably well-equipped password cracker. Could we write a function which just tells you yes or no? It's strong enough or not strong enough. And we did that. So that's fine. So for example, we said this is what's an 1116 characters at 1,000 gigatries per second. Is that strong enough for 100 years? No. So that's useful to know, isn't it? And the implementation turns out to be quite simple. So this is our crowdsourced password library. So it's looking all right so far, isn't it? So Thiago, perhaps we might start by thinking about what to do next. And one thing we could do is we could say, so we've been thinking about it from the point of view of the good guy, if you like, trying to generate strong passwords. What about if we flip hats and we think about it from the point of view of the bad hombres? people trying to crack passwords. How might we start thinking about going about that approach? You'd like to just, suppose we were to write a crack function, let's say. What would we start thinking about? Any ideas?
Well, the first thing I'm thinking is why you choose me to be the bad guy. But I'm
Yeah,
just kidding.
it's genuinely random.
So the first thing we need to know is the size, right, of your space. So
Yeah.
same thing, and then I think you to generate all possible combinations
Yeah.
of that string.
Yeah, that sounds like a reasonable first approximation, doesn't it? So we said, there is some space of possibilities, and we need to cover that, or, it'll take us a certain time to exhaust that space, but on average, we expect to get about halfway through it. And we talked a little bit last time, didn't we, about what order you might approach those keys in. So suppose I said to you, suppose I'm guessing, I'm going to think of a number between 0 and 100, let's say, and you need to guess that number. So Quinn joined us. So Quinn, suppose you're the password cracker in this case. What would you do when trying to guess my number? Where would you start?
And the numbers between 1 and 100?
Yeah, so we know it's somewhere in that space. So where would you start? Would you start from 0 and work upwards, or
start with 50?
Yeah, divide and conquer.
You're right, and then just split it up.
Yeah. So let's say I'm not going to be helpful to you by telling you that it's higher or lower than the number you guessed. So we can't play the high-low game. So does it make a difference even?
So if we can't get feedback, then it really doesn't. Yeah, I guess it doesn't really matter because every guess is sort of this independent.
That's right. So, but we might say, suppose, that naively, the easiest thing to do would be just start at 0 and keep guessing.
Right. Just crawl up. Yeah.
Bigger numbers. But suppose, as the password generator, suppose I know that. Suppose I look at your program on GitHub and I say, looks like Quinn's starting at 0. Seems to me like the best key I could have would be 100. Because it's going to take you the longest time to get there, isn't it?
Right.
Like, I know I can't prevent you from guessing it eventually. It's only a matter of time. So we've said there's really no such thing as a strong or weak password. You need to tell me what time frame you're thinking about before those terms have any meaning. So, but then suppose you said, so John's always going to pick at least numbers between 90 and 100, let's say. So what I'll do is I'll start at 100 and I'll count down. Does that help? No, it doesn't. Because I'll see your commit on GitHub and I'll say, Quinn switched his strategy. He's going to count downwards from 100. So now I'll pick really, really low numbers.
Did you just randomly pick?
Yeah. Yeah, random is the best.
That's really interesting, isn't it? Because when we were thinking about generating passwords, we were saying, obviously, the best thing to do is to pick them as randomly as possible. What we mean by random is unguessable, effectively, isn't it? Unpredictable. If I can predict what password you're going to pick, then it's no help at all. So it turns out the best strategy for generating passwords is to be completely random as far as you can. Also, the best strategy for cracking passwords is to be as completely random as you can, isn't it?
Mm-hmm.
There's a nice symmetry there, isn't it? So anything that I can know about the attacker's strategy is going to try and guess the password, that I can exploit that to make stronger passwords. Suppose I know that if you generate a password on Thursdays, it always starts with 1. then that dramatically reduces the search space, doesn't it? And similarly, as the attacker, anything you know about my generation strategy, so that's what I just said, isn't it? But you see what I mean? So, you know, we want to not have any information about each other to generate optimally strong passwords or crack them optimally quickly, either way. So what does this suggest to us about way? I mean, clearly we both need a source of really good randomness, because whoever has the weaker randomness source or the less amount of randomness is going to lose. So it's a war of randomness, isn't it? And we looked at increasingly random ways to generate numbers. One of them being math rand in Go, which we seed with some starting value and then it deterministically evolves that number. So the question is, how good is your seed, you know? And then in crypto rand, it's exactly the same thing, but just more. So, you know, more difficult to determine given the seed. And we said that most operating systems have some sort of source of randomness, or entropy, if you want to call it that, same thing. Like, you know, disk and user activity, people typing on the keyboard. If you ever generated an SSH key, for example, it might well have asked you to type some random keys on the keyboard so that you're generating some randomness, doesn't it? Anybody had that experience?
Yeah.
So that's fine, but if someone, you know, you could imagine someone who has complete knowledge of everything happening in your computer, they probably don't need your password, but never mind, supposing they had that, they would be able to know it straight away, so your randomness would disappear. We found actually there is a source of true randomness in the universe, if you like. If you think about it in terms of a password that even God couldn't guess, you know, for God, substitute someone with total knowledge of everything. And we said, yeah, there is, because quantum mechanics has, you know, in principle unpredictable measurements, if you like. So one thing we could do is say, make some quantum measurements, just look at the outcome. So if we measure polarization of a photon, its spin up, spin down, whatever. That gives us a binary bit that we can use for randomness. So we actually have that. There's various of these devices available hooked up to the internet. I've got a library to use one of them to get a source of randomness. So we can generate optimally strong passwords, if you like. We can also, we now know we can crack them optimally too. So that's helpful. So if we think about the cracking time, let's say, we might like to answer a few questions, mightn't we? We might like to know, you know, if my strategy for cracking a key is just to brute force it, and let's say I try the obvious things like the name of the person's dog, you know, their birthday, all of these things. I'll obviously try those first. We're still enumerating the same keys, we're just doing them in a more logical order. So we could actually write that function, not necessarily the random one, but just a dumb version that just starts from 0, let's say. And we might also say, suppose we thought about this originally in terms of a password validator, didn't we? So user sets a password for themselves, and we want to be able to tell them, no, sorry, that isn't strong enough. So let's think about, and we also need to say, we need to give them more helpful information than that, don't we? We need to tell them, sorry, your password is not long enough. Please make it at least 14 characters long, let's say. So Thom, if I can call on your expertise here, perhaps if we were thinking about this as a web service, let's say, maybe we've got some API, which if we give it not a password, clearly, because we don't want to send that over the wire, but just the length, let's say. We give them the character space, let's say it's the typable characters. And we say the user's password is 12 characters. Is that strong enough? Or we could ask what's the minimum length for a certain strength, couldn't we?
Yeah, I mean I work in a place where we do that.
Yeah, what would that API look like?
I mean, essentially, it's a validate endpoint on an API, and you pass in. There's kind of a bunch of different versions of it. We actually do have a version where we send in the actual password to
Right.
determine if it's in a list of passwords that have been stored somewhere.
Yeah, that's a really good point.
But like while you're typing, we do like validation like during typing so that the consumers of our API, the JavaScript application can just go, okay, well, I'm this far along. Have I met the rules yet?
Yeah.
We have configurable rules for each of our customers that use our API so they can set it needs to be this long or it needs to have this many characters or not these characters or whatever.
Yeah.
So the way it essentially looks is here's some details about the password and has it met the minimum requirements yet?
Yeah.
And those are essentially usually length, whether or not it has, and then whether or not it has some number of characters, right? Numbers versus capital letters versus other things like that.
Right.
And for us, that's configurable because we have a lot of different types of customers who use our API.
Yeah. That's interesting. Yeah, I didn't know you'd done this for real, but because it makes sense that you have.
In general, it's not, it hasn't been, that part is not too complicated, right? It's just meet a set of rules. We're not worried about, all the rules are frankly somewhat arbitrary, right?
Yeah.
They're best practices based on, whatever security experts, are saying in the industry.
Yeah.
They have nothing to do with how long would it take for somebody to hack this password?
Yeah.
Other than presumably if you have some extra types of, randomness in there, it's going to take longer.
Yeah. Yeah, and it's sort of a difficult problem in general, isn't it? Like, because we've all had this experience where you try to set a password for yourself and the site says, no, sorry, you need to include at least 8 numbers, 6 special characters, and 5 uppercase letters. And we're like, that's actually really awkward because the password I wanted to set doesn't have those properties, right? So it's a bit annoying. And we can actually see that some of those rules are kind of counterproductive. Like, if we think about it purely in terms of the key space, and I said to you, okay, all you know about the password is that it's 10 typable characters, let's say. Okay, you know the key space and the median crack time, that's fine. But now I tell you, okay, that contains at least 1 digit. Well, what effect does that have on the key space that you have to search? Well, it's clearly smaller, isn't it?
Yeah, that's true. It is. If you know that about the requirements, if you know the requirements.
Yeah, exactly. And you have to assume that they will, because they can go to your website and try to set a password just like anybody else, so they can discover those requirements. So while we're setting out with a very well-meaning idea that like we think this is going to make the password stronger by requiring something about it, in fact, we just made it weaker. So we would have done better just to say nothing, wouldn't we?
Yeah, I happen to think that something that says that the particular thing that goes and looks up the kind of databases of cracked passwords is probably better overall, because if you provide something like, hi mom or something like that, or spot my dog, or I don't know, then that's likely to have been stolen somewhere along the line. So it's better like that, at least then you don't have, the space could be anything, and that database is available to anybody to look up, so it's not like it's private information returning something that says, hey, don't use that password.
Yeah, exactly. So Adebayo, now I know you're working on a quantum password generator. We talked about this last time, I think, and you're using the quantum randomness source from my QRAND library, but that sort of doesn't matter, does it? It's you treat it as a source of good randomness, and that's about all. So you are trying to generate strong passwords, aren't you?
Yes, that's what I'm trying to do. Good day, everyone.
Welcome aboard. And the thing about that is, again, you're facing the same sort of issues that we have here, aren't you? So given some set of characters to generate from, or we established last time that the key space is the power, so the number of possibilities for each character raised to the power of how many there are. So clearly, whatever we can do to increase either of these numbers is going to increase the key space, and so it's stronger. So increasing this number would be good. So like if we said it can be any Unicode character, so that's 32 bits worth, but in fact not all of the Unicode space is used. So I think there's about 150,000 code points. That's great though, isn't it? That's a lot more than 100.
Mm-hmm.
So instead of 100 to the power of n, it's 150,000 to the power of n, which is bigger. But if we can increase this number, that gives us much more value, doesn't it?
Yes, it does.
Because we're exponentiating that number. So if we raise that number, the result gets bigger a lot more quickly than raising this number. That sort of seems intuitively right, doesn't it?
Yeah.
So and what we're saying is, if password rules, if you want to call them that, like must include one uppercase character, they're reducing this set in some way, or they're saying, suppose you have a 2-character password and one of them has to be a digit. So now your key space is typable characters to the power of 2, to the power of 1, times digits, which is 10, let's say. So that's smaller. So, reducing the character set reduces your key space, but not by a massive amount. Not enough to be seriously worried about, but nonetheless, most people would probably be horrified to realize that their carefully chosen password rules are actually making people's passwords weaker, wouldn't they? This is a good lesson for us, isn't it? If we're ever writing web apps or anything that enforces rules on passwords, just don't do that. If you do nothing at all, that will be stronger than anything you could do. Any rule you impose only weakens the passwords. But Tom's point.
I do
That's
have
a really
question.
good point.
Yeah, but I was going to say, Tom, you made an equally good counter argument, which is, as I understand it, that if left to themselves, people will pick weak passwords like dictionary words. If you include a rule that automatically eliminates all of those, like it must contain a digit, that can't be any dictionary word, then you don't make the password stronger, but you maybe make it take slightly longer to guess, if people are cracking passwords by starting with a dictionary.
The median crack time will get longer.
Yeah.
Presumably when that happens.
That's right.
What's interesting is that in this realm of, or at least my experience with this type of a thing, is when it comes to customers you might work with, right? So if you're going to implement a system that checks passwords and people are interested in security, what I found is that it's as much the perception of what is secure versus what is actually secure that is profitable in the market. And I work at a place that happens to be very security minded because we deal with financial data, but we are constantly having to tell our customers, no, you can't do that.
Right.
Because that's going to be too insecure. We won't support you.
Yeah. I think Bruce Schneier has this term security theater, doesn't he? Where it's like the appearance of security is more important in some cases than actual security. Sometimes both. You need both.
I mean, people want like, you know, what's your mother's maiden name, and as questions in their you know, they're like, why don't I have that? Why do you make me do this thing? This I have to get a token outside of my, you know, my computer. Why can't I just answer this question? Well,
you should just look up their mother's maiden name and send it to them, shouldn't you? And say,
I mean,
that's why not, because this information is easily available.
That's right. It's just it's a less secure password.
That's right.
Is what it is, and your password's already crackable.
That's right. So we have to sort of say, suppose, you know, we're thinking about it in really general terms, if we like. So, you know, suppose we sort of just punt the whole question of whether it's easily guessable because it's a dictionary word, or, you know, the most common passwords that people try, like, you know, 1, 2, 3 and Fred and so forth. So if we eliminate all questions about ordering of guesses and just say, you know, so we have no rules whatsoever, no cribs, we just have to brute force this key space, which is bigger or smaller. And so we're sort of getting to the idea that, like, maybe any rule or restriction that you can place on passwords might seem to help, unless the enemy knows them, which you can be pretty sure they will. So you actually want them to know as little as possible about what this key space looks like. Now, Evanson, aka Mr. Parish, is with us. Now,
Hello. Hello, guys.
I wonder what you think about this question of, you know, if you're validating passwords for strength, we can say, okay, we can calculate the median crack time and the key space and so forth, and that's fine. But what rules could we put on the password which might be useful, make them more secure, let's say? Is there anything you can think of? And it can only really relate to these two numbers, can't it? I just want to take a moment to tell you about a series of ebooks I'm writing for Go beginners called For the Love of Go. In book 1, Fundamentals, I show you how to write tests in Go and how to build programs test first. In book 2, Data, I tell you all about variables and values in Go and data types like slices and structs. If you're new to programming or just new to Go, I'll show you everything you need to know to start building fun and useful projects. Go to bitfieldconsulting.com/books and enter Code Club at the checkout to get 25% off now. So we've said, you know, the key space is a function of your character set and the key length. So we've talked about restrictions on the character set, and we've decided it's a bad idea to make that smaller. We could make it bigger, but then it's hard for people to type the characters. Strictly speaking, they should be using a password manager, shouldn't they? So they should just be copying and pasting. So actually, Adebayo's quantum password generator should probably generate random Unicode characters. Like they could be all Chinese characters, for example. That automatically makes it a bit harder to type, but it doesn't matter.
Yeah, but you know, we discussed the issue of portability, you know, across different regions.
Yeah.
Some
indeed.
of the character sets might not be available.
Yeah, that's right. And you can guarantee that somebody out there is not handling Unicode. So if you paste Unicode characters into their web form, it's probably going to crash, or, you know, if anybody watching is rushing to their code base to check whether or not that would crash their password system. Great. But yeah, so Mr. Parish, we were saying so we've talked about changing the character set number. What could we do about the length number?
I think perhaps we could, I don't know whether we've done that already because last time I joined a little bit late. Perhaps we could increase the length of the key.
Yeah. Yeah, that sounds right. Clearly, longer keys equals a bigger key space, and so therefore it's longer to crack. So suppose we said something like your password must be at least 15 characters long, something like that.
Yeah, that makes sense, but don't you think that's a little bit too long of a password?
No, I think that probably is a workable minimum, isn't it? I saw some figures a couple of years ago with there's a little table you can find floating around on the internet with something like median crack times for a given length of password, and 7 or 8 character password is crackable within seconds with a consumer grade laptop. So no use at all, essentially. The nice thing is every character you add multiplies the key space by 100, which is great. So, if it takes a year to crack a given password, you can make it take 100 years by adding another character, which is great. So that suggests we're not good at visualizing exponential growth, but it sort of suggests to us that the lower end of the key length is not going to be worth looking at, and the higher end is going to be great, but there's going to be a sort of a sweet spot, isn't there, where it very rapidly gets strong enough for all imaginable purposes, and then adding more characters really doesn't make a whole lot of difference, does it?
Yeah, sure, I agree.
Like if it takes 1,000 years to crack your password and you're like, nope, that's too weak. I need to add more characters. I need it to take 10,000 years before they crack it. Well, that seems unlikely, doesn't it? If it's safe for 1,000 years, I won't be around to care about it. So that's probably fine. So minimum length sounds like a promising one. So what effect does this have on the key space? Thing is, one thing we sort of forgot is that if you have a 10 character password, sure, it's x to the 10, but the passwords could also be less than that, couldn't they? So I mean, if you have 10 slots for characters, let's say, you might not use all of them. So let's turn it around and say if you know that the maximum password length is 10 characters, then you have to guess all the 10 character passwords, but you also have to guess all the 9 character ones, don't you?
I'm thinking if we increase the length of the key is synonymous, is almost equal as increase. It will be actually the effect will be that we will be multiplying the power, the exponential value of the will be actually I'm doing a mathematical sum here. Let's say we have like 2, let's say our typeable characters are 2, right?
Yep.
And the length of the key is 2. So
yep.
that
So
will
say
be
it's
2,
say it's bits.
2 to the
So 0 or 1, we've got 2 bits. So 4 possibilities.
So 2 will be the base, 2 to power 2.
Yep.
Since 2 to power 2, the length of the key will be the exponential, right?
Right.
And
so
then let's say,
yeah. So what I'm saying is we sort of forgot when we were developing this code, or we said, the password length is n, but we said it's exactly n. So, it's exactly 10 characters or whatever. So as the cracker, that makes my life a lot easier, doesn't it? I know I only have to guess all the 10 character passwords, but that's not how real passwords work. You might enter just a couple of characters. So actually what you're saying is it's the key space of the 10 character passwords plus the key space of the 9 character passwords plus 8765431. So actually, if we have a minimum length rule, that's actually reducing our key space again, isn't it? It's saying, hey, Mr. Cracker or Ms. Cracker, you no longer have to worry about the 1 character or the 2 character or the 3 character passwords. You have less possibilities to try. And again, that's a bit counterintuitive, isn't it? We started out with something which it seems like should make the password stronger, but we just ended up making it weaker again, which is nuts.
Sure. It's actually counterintuitive.
Yeah. And it's not like we can't think our way through this stuff because it's not super complicated. It only demands that you actually sort of spend a moment reasoning about it. But I think people probably don't. And this is why you see so many sites with daft and counterproductive password rules. But, sorry, go ahead.
John, I've seen something interesting. Sometimes I try to enter a password on systems. If I enter more characters, it says, okay, it's a weaker password. If I reduce characters, it's a strong password. And
it just sounds like a bug, doesn't it?
It's just, but it's kind of intuitive. Basically, for example, I was playing with some password. I put in the year, for example, 2020. It's a weak password. But if I reduce it to 20 at the end, it's a strong password. So I'm not sure how those people check at that time. It's probably lesser characters in that length, but it's a better password. So I don't know if they're checking some systems in there or something, or patterns not there because they say, okay, right, correct letters, numbers, uppercase, lowercase, special characters. I have a mix of everything. But still, I've seen this happen at multiple websites.
Yeah, and Thom mentioned some web services or libraries and things which sort of validate the password for you, and that's where I started as well. As I was looking at a Go library which purports to validate passwords, and one thing they were doing was saying, you know, they had rules in there which says if it contains numbers, automatically consider the password stronger. And I thought, yeah, I see what you've tried to do. But again, the problem is if the attacker knows that the password must contain a number because that's enforced by the website, then it doesn't help you at all. Not only doesn't increase the strength, it actually reduces it. So that really sucks. So if we were going to write a good password validation library, which I'm sure we would, we've made a start here, haven't we? Because we've ignored all of that stuff. We just said, forget the digits and the ampersands, dude. Just tell me the key space. You know, you can't argue with math, can you?
Oh yeah,
Well,
absolutely. Yeah.
You can, but math will win. So that's good. So I don't want to waffle too much. You know how I love to waffle. But I just thought it was sort of funny and interesting, isn't it? How attempts to, well-meaning attempts to beef up people's passwords tend to not work that well. But let's think. So we said, you know, Parish had a good idea. One rule that actually might be worthwhile is a minimum key length. And I totally agree with that. I mean, I feel intuitively that must be helpful, even though it technically reduces the key space. How much does it reduce it by? In fact, not a lot really, is it? You know, if we think of the 10 character passwords, we know that space is 10,000. What's the size of the 9 character password space? It's 100 times less. So it's only 1% of the big key space. And then, you know, the 8 character passwords are 1% of that, and so forth. So they very rapidly, exponentially drop off to not being worth considering, don't they? So we could say, suppose you added a minimum length rule. How much does that reduce the key space? The answer is 1% and change, isn't it? something like that. So actually, to be able to prevent people from typing in 2-character passwords, let's say, that's well worth it, isn't it? It's like, if we assume, let's say, maybe the median length is 5, as we've established, that's absolutely rubbish. It's more or less useless. So if we can eliminate those passwords, that has a huge effect, because now, okay, we only have 10-character passwords, but those are already, many, many orders of magnitude more secure. So that's all right. That's a deal I'll take, if you like. So actually, that was a very good idea, Parish. I'm sorry I appeared to criticize it, but it's important that we know what the deal is, isn't it?
Sure, I agree.
So that's fine. So we have some ideas about key space and so forth. So let's try and write some code, because it is Let's Code Club. What should we write? Should we try to write a crack function, let's say? So should we actually do some password cracking? It's time to stop theorizing and time to actually do something. Umang, perhaps you'd help me here. We should start by writing a test, shouldn't we? And that'll help
we
us sort
should.
of.
John, I have to drop off, so I'll sorry have to pass the baton to somebody else.
Oh, that's okay. Yeah, just nominate another victim.
Parish, how about you, Mr. Parish?
Well, let's see what I can do.
Yeah.
Sorry about that.
No worries.
No problem.
Glad you could join us. So, well, we know how to start a test, don't we? It's going to be test something.
Yeah.
And let's say we're calling it crack.
Yeah.
So this is all standard. So our want will be something, our got will be something, and we'll compare want and got. None of this will surprise any BIT students. So how should we think about this? So we know what our got's going to be, is we're going to call key.crack some parameters, perhaps. And let's say we start off with a known password, like let's make it a really short one, so it's easy to crack. In fact, let's make it a number, because that's just going to be easier. Let's say it's 99, and we'll just work with numbers, but we understand we can generalize this to strings, right?
Yeah.
So what do we need? So assuming we want crack to not only work with numbers.
Okay, I'm thinking we could pass up, we could have an argument, or rather a parameter called guess, which is your password you're trying to guess.
Yeah.
And maybe a flag called try rate to limit the number of guesses that you can possibly guess in a given time period of time.
Yeah. So one thing we would like. Yeah, I mean, we're testing here, but in real life, if we're really cracking people's passwords, we won't actually know the password in advance, so we can hardly pass it in, can we?
Yeah, sure.
So suppose we said something like crack is some completely general thing that is it's got to have some way to try passwords, and we will supply it with a way of knowing whether or not it's guessed correctly, because only we know what the right answer is, 99 in this case.
Yeah.
So we'll park that to think about for a minute. And what other information does it need? So we give it, let's say, the function we give it is called something like check. you know, check if this is the right guess.
Yeah.
And what else do we need to give to crack? Any thoughts?
I'm thinking, since we are kind of like brute forcing, I think it could be, it makes sense if we give our crack function a number of, you know, a limit to how, if it's going to brute force, how many times do I brute force before giving up? Kind of like
Yeah.
a try rate, so that you don't exhaust your resources.
Yeah, in practice, we would need that, wouldn't we? So we'd need to say,
Yeah.
maybe this key is just like a million bits long and it's going to take us a while and we don't have time. But let's flag that as future enhancement for now and just say, suppose we just literally brute forced it until either we die of boredom or the computer runs out of battery, you know, one or the other. So we're just going to keep on trying until we get it. So what else does crack need to take?
I think then, if that's the case, what about the key space?
I'm just going to sort of hand wave here and just say, one argument it needs to take is a way to know if its guess is correct. And yes, what was the other one? Sorry.
The key space, like for instance, one has 2 digits, so you tell it to guess, but I'm thinking the password should have 2 digits. I mean, kind of like giving it a way of knowing, like, if the guess is correct.
Yeah, that's right. But in real life, you wouldn't know that, would you? So you just say, I
Yeah,
just
you
have
wouldn't.
some, you know, suppose somebody gives you a zip file and they're like, you know, the answer to the ultimate question of life, the universe, and everything is inside this zip file. If only you knew the password, well, get cracking, sort of thing.
Yeah.
If you knew it was a 5-character password, well, that'd be super helpful. But we can't hope to get that lucky, can we? And if we're being smart about our password rules, we won't have enforced that. So we're sort of working our way towards thinking that we need to tell it how to guess, don't we?
Yes, yes.
Like, we happen to know that it's a number, so therefore we might brute force by just trying increasing numbers, but it knows nothing about that. We need some way to sort of communicate to it, okay, here's what you do to generate a new guess. Is that a productive way to think about it?
How about maybe we give it, I'm thinking like, I'm thinking about a regex, but I don't want to pass a regex.
Yeah,
like,
neither do I.
Like tell it, I'll find a way of telling it that you can look for the password inside this set of characters, between this set of characters and this set of numbers.
Yeah, and in fact, that's a more specific version of what we already said, isn't it? So we said if we have some way of generating guesses, let's say, well, let's say some way of generating next try.
Yeah, yeah.
That's completely general, isn't it? Could be alphabetic passwords, could be numbers, could be bits, could be hashes, anything. So that's really useful. So I think we have an idea about what crack needs to take. Now, Quinn, can I call on you here? Because I have a sort of feeling that you're well placed to know what kind of thing we might want to pass to crack to do this. Can you think out loud for me maybe about what we could do here?
And we want to the information on where to go, like what to do next.
Yeah, so we're almost saying we're not actually passing data as such, is it? We want to pass some logic. How could we do that?
May I?
Oh, through like a function.
Sounds like a function, doesn't it?
Right.
Yes, Thiago, you wanted to say? Is that what you're going to say?
No, I was going to say the the data type, password, what data type it is. But yeah,
Yeah,
I'm not
absolutely.
going to know
And in
names.
fact, that's part of this, isn't it?
Right.
So if as Quinn said, that's a function, this is also a function. This is one reason we love Go, is we can pass functions to functions. Never get tired of that, right? So that function will include in it what the data type is, isn't it?
Right.
So you know, if we're working with numbers, then can we zero in on what the signature of this function is going to be? Well, Quinn, can you help me zero in?
Sort of the func, you know,
Yeah, func definitely. A func taking what?
Probably if we're using a number like an int or float.
Yeah.
Um,
Yeah, let's say we're only working with ints. We would love to have generic types, but we just have to be patient about that.
And then it's either gonna, I'm assuming it's gonna return some sort of error, maybe, right? Like, you know, like if you guess wrong, then it errors out and be like wrong,
Yeah.
or it returns nil.
That
right?
works.
Yeah.
So yeah, so nil would mean guess is correct.
Right.
Some non-nil error value would mean it's wrong, but actually then if there's only two possibilities, we don't really need the error type, do we? It just sounds like bool, doesn't it?
Yeah, exactly.
So we say, you know, if you have a certain guess, let's say 3, well, pass it to this function and it will tell you Booleanly whether you're right or not.
Right.
So let's call that check.
Yeah, I was thinking of it more kind of you know, like if we were wiring it up to an app, that it would probably give some exit code. But like, yeah, for purposes of the test, I think bool is better, right?
Yeah, let's see if this will work. So okay, can we do anything with this one? Let's call this next try. So it's also a func. So what does that take? Any thoughts?
Takes some sort of
Well, let's think our way through it. If you know, suppose we start from scratch and we say, okay, call next try. Well, what does next mean? You know, next sort of implies that we are somewhere, doesn't it? So maybe that's giving us a clue. That this function could say, given some guess, what's the next guess?
Right. I'm assuming that it's going to be some modifier on the int, right? Like kind of.
Yeah. Well, suppose we have it taken int, saying this is my current guess. I guessed 3. I called check. It told me that was wrong. So now I want to know if I'm on 3, what's my next guess? So what's my return type for this function?
Int.
Yep. Makes sense, doesn't it? Okay. So that's great. So Andrew is also with us. I don't want to leave you out. Maybe you can help us. Can you help us write one of these functions? So let's say, should we try to write the check function? Let's put it here. Let's just define this as a func that takes int and returns bool. Okay. What can we do here? Any thoughts?
Hi.
Howdy.
Someone hopping in? Oh,
okay. Yeah, I'm here. Sorry, everyone. I'm trying to look at this code in GitHub and get familiar with it a little bit. This is my first clubbing code.
Great to have you.
Thank you.
So yeah, don't worry, you're not on the spot because we're all just trying to put our brains together to figure this out as a group. So every extra horsepower you can add is very welcome.
Sure. Well, I guess we just need to figure out what to do with that int parameter. Where's that going?
Yeah, let's be the computer and think about it. So if I give you a guess, say 45, so you're the check function. How can you check if that guess is correct?
To look at maybe these other functions we have. We have to have some system to check it against.
Yeah. So you're saying we need to name our argument so that we can refer to it. So we're saying if guess and wave is right somehow.
I guess if it's what we want, if guess
Yeah.
is equal to want, then
Yeah.
it passes.
Then return true.
Yep.
Yeah. Else return false. My students are laughing here. They know this isn't how this is going to end up. But yeah, if guess equals want sounds right to me. Can we refactor this a bit?
Yeah, you could take out the else because you would already returning.
Yeah, good man. That's good. Can we do even more though?
I mean, you could just say return guess equals want.
Yeah, sounds good to me.
You need a if.
Yeah, everybody happy with that?
Yeah.
Yes.
It's rather elegant, isn't it? You'll never write else again, will you? So fine.
Myself to not do that.
Yeah. So we've done that. That's great. Can we write next try then? It's a func that takes an int and returns int. Fine. Okay. What do we do? Given, so again, let's name our parameter. Given guess, what can we do to generate the next guess?
I guess.
Yes, plus plus.
Yeah.
Sorry.
Yeah. Yeah, that would work. As long as it's not, the same as guess, right?
Right. But of course, we need to return this. And actually, that doesn't work because guess plus plus is not an expression in Go, it's a statement. So the distinction between those two things is sort of boring. But what it means is we could do guess plus plus and then return guess. But that's, well, let's just do that.
Let me ask, could we use an named return value?
Yeah, we could do that. But maybe we don't need to, because maybe we could just return guess plus one. It's kind of the same, isn't it?
Yeah.
That doesn't look too bad, does it? Actually turned out to be fairly easy to write these functions. So we'll pass next try. Okay. Let's join these up. So, okay, are we there yet? Are we done? No, because I can't type. What about now? Looks all right, doesn't it? We haven't written the function yet, sure, but that's probably going to be pretty easy, I would think, isn't it? If we're used to working TDD, it almost always takes us a while to write the test, and then actually implementing the function is relatively easy. So should we have a go? Adebayo, can I bring you back in? Resident password expert. Can we try to write this function now? So what do we need here?
Well, we need the input from the user, that's the guess itself.
Yeah, we need somewhere to start, don't we? So that's an interesting point, but let's just write the function signature first. So actually, we kind of already decided this, didn't we? We said it takes a function. It takes a function that takes an int and returns a bool, and it takes a function that takes an int and returns an int.
Okay, yeah.
So I like writing things like this, and you can see that you wouldn't want to have too many of these or have them too complicated signatures, because it just starts to look alien, doesn't it? Starts to be really hard to just parse function signatures like this. But you could imagine, couldn't you, that we could pull this out into some sort of named type like this, and
Yeah.
and the other one would be next try func.
Right.
You know, if it's easier for you to think about it in these terms, we can do that. So now crack takes a check func and the next try func. And we see these kind of things in the standard library, don't we? So like in HTTP, for example, you've got handler func, which is a function that takes the HTTP response writer and a pointer to request and doesn't return anything. So this is kind of the same idea. So fine. So you said we need to start somewhere. So let's make our first guess 0. we're doing the dumb strategy that that we already know. You know, the defender mustn't get hold of this code, must they?
No.
Because we already worked out that they would just start making all their passwords 99. And you could sort of imagine double bluffing them, couldn't you? Like, okay, then we're going to guess 99. but let's keep it simple. So what's next?
Yeah, we pass that to the two functions.
Yeah, we need to, let's call them check and next try. We're close to running out of time, but I think we can do this. So we need to try our guess, don't we? It might be 0. We could get lucky. So let's check it. And if so, return guess because it was correct. What do we do next?
But we have no return in the function signature.
That's very true.
Yeah, that's why it's flagging.
Yeah. Your side job is actually a Go compiler, isn't it, Thiago? You're good at catching these things. So we should return what? Int. Yeah. Sounds reasonable. Okay. So what do we do next? So we guessed 0. That was no good, let's say. What's next?
If that doesn't work, then we have to call the next try.
Yep. We know it takes guess and it tells us the next guess, so we can just reuse that variable. It's not colon equals. And in fact, we just want to do that forever, don't we? We have no limit on the number of guesses, although that would be a nice feature to have. We just basically say, is it 0? No. Okay, next. Is it 1? No. Just keep going until we've done it. So are we there? Is that all?
Yeah.
Let's try it.
Looks like.
No, but that's only because I can't write Go, apparently. This should be D, shouldn't it? Okay. Awesome. Okay, did that work? Suppose we start the cracker off at 100, then it's unlikely to guess 99, isn't it?
Yeah.
So if we run the test out, it won't fail, but it'll probably just time out. Yeah. In fact, test timeout after 10 minutes by default. But if your tests are taking that long, you've got serious problems already, whether or not you've got an infinite loop. So modulo some way of giving up. This seems pretty good, doesn't it? And we could even have it return the number of tries or something like that if we're interested in that kind of instrumentation. But whoops. Oh dear. Oh, test timed out. Yeah, individual test times out after 30 seconds. So fine. So that should work. Okay, good. And I think can we feel happy that we can sort of generalize this idea to, let's say, string passwords or binary keys or TLS keys, something like that. I mean, we're a bit limited by the type system here, but we could imagine, because we used Quinn's super functions here, these functions could in fact be anything. So you could imagine, instead of just checking some value, this could be a hash, for example. So maybe we have the SHA-256 hash of the password because we dumped the passwords file, and we wouldn't be able to dump it from one of Thiago's systems, I dare say, because security. But suppose we could. Suppose we bribed him to give us his user's password file. And we could just do like SHA-256 sum of our guess and compare it with the hash we have. And then next try is maybe just some completely random way of doing it, as Parish was saying. You know, we wouldn't want to just guess linearly from 0 upwards. That's too weak. We would like to randomly sample the key space using perhaps quantum randomness. And we could do that, couldn't we? So great. I think that's a success. That was a lot of fun.
Yeah, that was fun.
Is there anything serious that we missed out, or any questions?
Maybe a suggestion, maybe.
Yeah.
Rather a question.
Yeah.
I'm thinking maybe in later stages when you're refactoring, would it be wiser if the guess would be supplied by the caller of the crack function? The guess variable inside the crack implementation.
Yeah, you mean you could say start here, for example.
Yeah.
Here's your starting value. Yeah, that's a good idea.
Should be the first parameter.
Yeah, or maybe you could imagine giving some indication of what the key space is that you need to search. You know, in order to help you, maybe you need to figure out how to optimally search that key space. That could be helpful. So yeah, good idea. So you could imagine turning this into a real production password cracker, but I think we've got the essentials, which is great. So we learned how to generate passwords, and then we learned how to crack them. So I think we're done with passwords. So thanks very much to everybody for being here. Thank you, Parish.
Thank you. Have a great day.
Yes, thank you.
Thank you, Adebayo.
Thank you.
Thank you.
Thanks, Quinn. It's been good to have you.
Yeah, thanks. Good to be here.
And thanks, Andrew.
No problem. I enjoyed it.
This was a lot of fun. I hope to see you all next time.
Yeah.
Bye.
Bye-bye.
Yeah, bye. Bye-bye.
Bye.